Okay, get ready for the boring. It's math. It is not something I enjoy teaching, but that doesn't lessen its importance, especially in this area of population biology, where one of the most important things you do as a population biologist is you try to monitor what a population is doing over time. Are its numbers increasing? Are its numbers decreasing? If it's an invasive species, is it exhibiting an exponential growth pattern, and it's going to be a major threat? If it is some other species, is it in decline? Is the ecosystem in trouble? It's really powerful math, important math for population biology. That said, it's not a whole lot of it's not a real fun thing for me to teach, but it's not difficult. You kind of just learn where to plug in the numbers, and you're good to go. So that said, um, basic points, already kind of talked about those. By the way, just print out this sheet if you're someone who likes to kind of scribble around. But what you really need to do is understand this material and then use it to solve some population biology problems. So your basic points, predicting and analyzing changes in population sizes. So math is the one tool we have where we can really use that to help model what is happening or what might be happening in an ecosystem, and make predictions for the future, which is, again, very valuable to be able to do. There are basically four things that affect population growth. And when we say growth, that can mean obviously increase, but also decrease, just population change. New organisms get born, they die. Immigration, coming in, just moving into an area, or organisms leave an area. All of those things affect the population size. We are going to focus on birth and death in this. Okay. Now, basic equation concept for this is that the change in population size over some time interval, usually it's 1 year, but it can be any time interval that you're asked about, that you're interested in, that the problem asks you about. So change in population over some unit of time is going to basically boil down to how many births you had during that time interval minus the number of deaths you had during that same time interval. So if it's over a year, how many were born, how many died, and that's going to basically give you, sorry about that, your change in population size. Now, a way it is more commonly expressed is like this, okay? Where big N is your population size when you start observing, when you start monitoring. Little t is the time period. This is change in. So change in the population size over this time period, this 1 year period, is usually births minus deaths, where big B is the number of births, big D is the number of deaths. Okay. Now, the thing we need to understand, though, it is often expressed, the births and deaths is expressed in terms of being per capita, meaning the average number of births and deaths per individual during some period of time. So usually this is going to be some decimal number often. Okay, so your per capita death rate is symbolized. I'm sorry, did I just say death? Birth rate per capita is symbolized as a little b. Per capita death rate is symbolized as a little m. So just be aware of that. Now, we usually use per capita birth and death rates, little b and little m, to calculate the number of expected births per year in a population of whatever size you have. So this stuff right here, you may use it, but not a whole lot. What this right here is doing, though, is showing you where some of the equations are coming from that are going to be more of use to you. But big B, number of births in the population, is going to equal the per capita birth rate times the number in the population. Same goes for death rate. Okay, the big D, number of deaths, is going to equal the per capita death rate times the number in the original population. Now, this is the population growth equation, okay? So change in the number of organisms over the course of, say, a year's time is equal to the per capita birth rate times the number in the population minus the per capita death rate times the number in the population, okay? Now, ecologists tend to be most interested in the difference between the per capita birth rate and the per capita death rate, because that is really going to tell you, are we growing, are we shrinking? And that's a obviously simple little equation, okay? It is this one right here, the per capita rate of increase or decrease, as the case may be, is little r, okay? So it's the difference between the per capita birth and the per capita death rate, okay? And the value of r is going to basically show you truly is that population growing or declining. If it's bigger than 0, it's growing. If it's less than 0, the population's declining. If it is 0, then you are experiencing 0 population growth, okay? Birth rates, per capita birth and per capita death rates are equal at that point. Births offset deaths, okay? Births and deaths still occur, but they balance each other out exactly, okay? Now, now we can rewrite this equation for change in population size as follows. We can rewrite it as change in the number in our population over a certain period of time is equal to that little r times the total number in your population, okay? Now, this is straightforward, simple. Real ecologists usually aren't so terrified of math as I am, and they use differential calculus, and they phrase this very equation here like this, using these d's instead of the delta sign. It makes no difference as far as we are concerned. The equation works exactly the same way. Just know that you will see it with these little d's as opposed to the deltas sometime. I think that's how it's shown to you on your formula sheet on the AP exam, okay? Now, this is where we really get to plug into what is probably going to be used most for you in terms of population problems. The two types of growth rates, exponential growth and then growth when we hit carrying capacity, okay? So how do we examine exponential growth when we look at population growth, okay? To analyze exponential growth, first of all, we need to know what it is. We know that it's when the population is growing without limits. So that means it must have abundant food, no shortages, and the population members are free to reproduce at the fastest rate they can possibly reproduce at. Under such conditions, we assume that the per capita rate of increase is the maximum rate possible for the species, okay? It is known as the intrinsic rate of increase, and we report that as R max. So what's the fastest rate possible for this species of organism to reproduce, okay? So that's going to lead us into an exponential growth direction. So the equation for exponential growth in a population is just what we've been talking about. Change in the number in your population over some period of time is going to be equal to this maximum growth per capita growth rate times however many are actually started out in your population. Okay? Now, the other side is logistic growth when you've hit your carrying capacity. So if exponential growth looks like this, where this is time and this is the number in your population and we're just shooting straight up. Logistic growth is where we have actually depleted some resource or something, and then our growth levels off and slows down. And our births and deaths are going to be much more close in number. Please remember that the symbol for carrying capacity is K. Okay? So, to examine population growth under logistic conditions, you just got to add in that carrying capacity piece, okay, that K. So again, the change in the number in your population from when you start to a year later is going to be equal to the maximum per capita growth rate times the number you started with, but then in parentheses the number at which carrying capacity would exist, which you would have to be given in the problem. So if your carrying capacity for my yard is 20 squirrels, okay, that's the most my yard can support. We would take 20 and subtract from that however many are actually in the population and divide it over that same number 20, okay? So that's, and then we multiply, obviously, this times that, okay? What I would recommend you do is you start trying to plug some of these numbers in. I have uploaded a simple problems sheet. Do those problems, bring them in with questions, and we will talk about it next time, well, whenever that time is in class where we get to this, okay? You'll see the due dates and all of that on Edmodo. And thank you for watching, and I'll catch you next time.